All right, let's dive into one of the heavy hitters in machine learning, something that sounds way more complicated than it actually is: support vector machines.
And yeah, I get it. Support vector machine, it definitely has that technical kind of intimidating ring to it, doesn't it? Sounds like you need a PhD just to say it out loud.
But here's the secret. The main idea behind it all is incredibly simple. And honestly, it's pretty elegant. Once you really see what it's trying to do, the whole thing just clicks.
See, at its core, an SVM is just trying to solve a really basic problem. Imagine you've got two messy piles of data points, let's say circles and crosses. Your job is to draw a line that separates them. But not just any line. You want to find the absolute best, most confident line you possibly can. So how do we find that best line? Well, the first big idea is to stop thinking about a thin little line. Instead, let's imagine we're creating the widest possible road between the two groups. I mean, look, you could draw a line right here, or maybe squeeze one in over here. They all technically get the job done. They separate the circles from the crosses. But an SVM is picky. It's not looking for just any solution. It wants the one that screams confidence, the one that puts the most distance between itself and both groups. And that distance, that widest path, has a name. It's called the margin. The entire goal of an SVM is to make this margin as wide as possible. Think of it as a safety gap or a buffer zone. The bigger that buffer, the more robust your model is, and the more certain it can be about classifying new data points.
Now, here's where it gets really clever. To build this maximum width road, you don't actually have to look at every single data point. Nope. In fact, most of them are totally irrelevant. The only points that truly matter are the ones sitting right on the edge of that margin. And these have a special name. They're the support vectors. They're the critical data points that actually support and define the entire boundary. They're literally the pillars holding the whole thing in place. And this shows you just how important they are. Watch this. First, take a regular point, one that's way off in the distance, far from the margin. If you move it around, nothing happens. The boundary doesn't budge. But now, take one of those support vectors. The second you move it, boom, the entire boundary has to pivot and shift to maintain that maximum margin. That's why the whole algorithm is named after them.
Okay, so far, we've been in a nice, clean, perfect world where all our data can be separated cleanly. But let's be real. Real-world data is almost never that neat. It's messy, it's chaotic. And this is why we have two flavors of SVM. The hard margin version is the super strict one we've been talking about. It demands perfect separation, no exceptions. But for the real world, we use the soft margin SVM. It's way more practical. It's flexible. It understands that sometimes to get a better overall boundary, you might have to let 1 or 2 points end up on the wrong side of the line. And we control that flexibility with something called the C parameter. Just think of it as a strictness knob. If you crank C way up, the SVM becomes a perfectionist. It will try to classify every single point correctly, even if it means creating a weirdly contorted boundary that won't work well on new data. That's called overfitting. But if you turn C down, the model relaxes. It prioritizes a nice wide, stable margin, and it's okay with a few outliers being misclassified.
Okay, now for the part that honestly feels a little bit like magic. We've been talking about drawing lines, but what happens when a straight line is just impossible?
Right. What if you have data like this, where one group of circles is completely surrounded by a ring of crosses? You can try all day, but there is just no straight line in this 2D world that can separate the two. So, are we stuck? Not even close.
This is the absolute genius of the SVM. It asks a brilliant question. Instead of trying to draw a complicated curvy line here in 2D, what if we could just look at this data from a different perspective? What if we could project it into a higher third dimension? Maybe up there, a simple flat sheet of paper could slice right between them. And this is done using something called the kernel trick. It's basically a mathematical shortcut, a super efficient function that lets the SVM figure out where that separating plane would be in a higher dimension without ever actually having to do the heavy lifting of calculating all those new coordinates. You get all the power of the higher dimension without the crushing computational cost. It's an incredibly slick solution. Okay, so let's zoom out and put it all together. What's the big picture? What are the main strengths and weaknesses of using an SVM?
Well, for starters, it's incredibly powerful in high-dimensional spaces, even situations where you have more features than data points. And because it only cares about those few support vectors, it's really memory efficient. Plus, if you tune that strictness knob right, it's fantastic at avoiding overfitting. It's just a great all-around choice for a lot of medium-sized classification problems.
But of course, it's not a silver bullet. When you get to really massive datasets, the training can get pretty slow. Picking the right kernel and tuning those parameters can sometimes feel more like an art than a science. And unlike, say, a decision tree, it can be a bit of a black box. It's harder to explain why it made the decision it did.
So, if you only walk away with one single idea, let it be this. Just remember that an SVM finds the safest possible boundary by focusing only on the most critical, most essential data points.
And that kind of leaves you with a pretty cool thought, right? This whole thing is about teaching a machine to find the most optimal, the safest path through a world of messy information. And if we can do that with data points, what other complex problems could we solve by just finding the safest path forward?